Okay, in this question there's quite a long preamble here, but it's talking about cubic polynomials of this form and corresponding cubic equations with one real root and two complex roots. Okay, so in parts A, B, and C, let R equal 1, A equal 4, and B equal 1. Consider this equation. Given that 1 and 4 plus I are roots of the equation, write down the third root. So this is pretty classic. We know that complex roots have to come in conjugate pairs, so the other root is simply 4 minus I. And those are the three roots altogether. Verify that the mean of the two complex roots is 4. Okay, that's like the average. We're going to add them together and divide by 2. So 4 minus I plus 4 plus I divided by 2 equals 8 over 2, which equals 4. So we've just verified that. Okay, this next question, we're considering this function. Show that the line y equals x minus 1 is tangent to the curve at this point. So we can basically get the tangent line here at this point, and it should be this. So to get the tangent line, we need the derivative, which gives us the slope of the tangent. We can expand it and then find the derivative, or we can use product rule, which is what I'm going to do. Okay, so we get derivative of that is just 1 times x squared minus 8x plus 17, and the derivative of that is 2x minus 8. So we have x squared minus 8x plus 17 plus 2x squared minus 8x minus 2x plus 8, which is 3x squared minus 18x plus 25. Okay, so now to find the slope at this point, that's just the, that is the derivative. Okay, so we'll just plug in 4, right? So f prime of 4 equals 3 times 4 squared minus 18 times 4 plus 25. And let's use our calculator for that. Times 16 minus 18 times 4 plus 25. We get 1, which is what it's supposed to be because the slope of this is 1, right? So now we can get the equation line, or actually we can just kind of just verify that this is on both of them. Alright, let's just plug in 4 and get the y value. So f of 4 equals 4 minus 1 times 4 squared minus 8 times 4 plus 17, which equals 3, and this is 16 minus 32 plus 17, which is 3 times negative 16 plus 17, which is just 3. So that is the y value at the point where it's tangent. So it is tangent at the point 3,4,4,3, and the slope is 1. So we can use point slope form. Y minus 3 equals 1 times x minus 4, and then you have y equals x minus 1 as required. In this next question, we are asked to sketch the curve and the tangent, clearly showing where the tangent crosses the x-axis. Okay, so let's draw a sketch. Alright, the tangent is y equals x minus 1. So it's going to start at negative 1 down here. Let's draw a couple lines here. So the line's going to go through here and here. It's going to go up the slope of 1. Okay, so that's the line y equals x minus 1. Now the curve, the cubic, has an x-intercept of 1. Okay, so the curve is going to go through 1, and it's going to be tangent at 4, 3. There's the point 4, 3. It's going to be tangent there, and it's got an x-intercept here. So it has to go like this. It's going to come down here and like just touch there. So something like that. So it's got a minimum there and then a maximum there. Okay, this next part, consider this function g of x. So this is more general. In part A, B, C, we were given the value of r, a, and b, but now we're looking at the general case, and we're going to show that g prime of x equals this. So let's just find the derivative of this using product rule, just like before. So g prime of x is going to be equal to, now the derivative of that is just 1 times, and it's going to be this unchanged, plus, so we're using product rule here, we're going to have x minus r, and the derivative here is 2x minus 2a. This disappears because it's a constant. Okay, so we want to show it equals this, so this part looks similar to this one, but the 2 is factored out. So that's going to be 2 times x minus r, x minus a, plus that, which is what's required in the question, right? Okay, the next part, hence or otherwise prove that the tangent to the curve y equals g of x at the point here intersects the x-axis at the point r0. So just like the specific example we did earlier, we got the x-intercept was 1, 0. Now we're going to get r, 0 because it's the more general case. So we do it just like before. We plug in the a value here into g prime of x to get the slope of the tangent at that point, right? So g prime of a equals 2a minus r, and this is a minus a, so that will become 0, and then we have, that's not x anymore, it's a squared minus 2a times a plus a squared plus b squared. Okay, so that's 0. A squared is here, and then we have, actually it's going to be a squared, and this is going to be a minus 2a squared, and then plus a squared, so all those cancel, and we just get b squared. Okay, and remember that corresponds to the slope of the tangent line. Okay, to get the equation of the tangent line, we need to do, well, we use point slope form again. So we have y minus the y value at that point is g of a equals the slope of the tangent line is that, and then we got x minus a. So that's the equation of the tangent line. So we need to prove that the tangent to the curve at this point intersects the x-axis. So we need to find the x-intercept. So we let y equal 0 at the x-intercept. So we get 0 minus g of a equals b squared x minus a. Alright, I guess we can actually get g of a. We should have probably done that at the beginning, I suppose. What's g of a? G is this function, so let's plug in a, or sorry, this function here. We got a minus, let's do it on the side. G of a equals a minus r times a squared minus 2a squared plus a squared plus b squared. Okay, so that's going to be, all this is going to cancel. We just get b squared times a minus r. So let's put that in here. We're going to have negative b squared a minus r equals b squared x minus a. We can divide both sides by b squared. And we got negative a minus r equals x minus a. So x equals negative a plus r, and then bring this to the other side, it's going to be a plus a. So we got x equals r. So therefore the x-intercept is r comma 0. Okay, this next question, this equation equals 0 has roots r and a plus or minus bi, referring to this a and b. Deduce from part di that the complex roots of the equation can be expressed as this. So yeah, the complex roots are a plus or minus bi, so they're basically saying show that b equals square root of g prime of a. And we just use that just use part di for that. So using, I should call that d1 instead of di. Using that, we have, and we actually did this before, we got g prime of a equals b squared. If we look back, g prime of a equals b squared. Okay, from that we can square root and we get b equals square root of g prime of a. Therefore, the complex roots are a plus or minus I root g prime of a. Okay, just substituting your value of b into this part right here. Okay, this next question, there's quite a lot of more information, but basically it's talking about this graph which shows a particular solution, this one here, where it's general like before, but we have this 16 here. Okay, and that corresponds to b squared, recall, so that means b equals 4. Okay, this question is asking us to find the roots of this cubic. Obviously one of them is negative 2. The two complex roots are, from our previous result, a plus or minus bi. And we know what the b is, we've got to figure out what the a is right now. And there's a couple ways to do it, but recall let's look at the equation of this straight line here. In point slope form, it would be y minus 0 equals the slope of that. One of our previous results we saw that this was b squared. So that's going to be 16 and x plus 2. So that's the equation of this line right here. Okay, so y equals 16x plus 32. And if we want to find out the a value, we put in 80 equals 16a plus 32. So we have 48 equals 16a and a equals 3. So now the roots, to answer the question, the roots are negative 2, a plus bi, so that's going to be 3 plus 4i, and 3 minus 4i. State the coordinates of C2. So C2 is below the x-axis, and it says in the preamble to this question that, well, basically C2 is a negative root g prime of a, which corresponds to the b value, right, in our complex roots. So it's just going to be, a is 3, so it's just going to be 3, comma, negative 4. In this next question, we have consider the curve. We're back to the general curve, not the specific one above. The curve has a point of inflection at point P. So if it's talking about point of inflection, we need to get the second derivative. We have the first derivative from before, so let's get the second derivative by getting the derivative of this. Let's use product rule. So 2x minus r times the derivative of that is just 1. And then if we get the derivative of this, it's just 1. So we're going to have this is the derivative. And it's going to be 2x minus 2a, and these are constants, so they cancel. We need to set that equal to 0 and solve for x. So we get 2x minus 2r plus 2x minus 2a plus 2x minus 2a equals 0. And solving for x, we got 4x. Actually, let's divide everything by. Now let's do this. Yeah, 4x equals, and then bring the other things to the other side. We're going to have 4a on the other side and plus 2r. Let's divide everything by. Oh, do we get 4a? It's 6a. 2x, 2x, 2x. So 6x. Sorry. So we divide by 6 and we get x equals 1/3 2a plus r as required. It's only a one pointer, but it's really tough to get the points in the answer key. It says, hence describe numerically the horizontal position of point P relative to the horizontal positions of R and A. So point P is somewhere along here, the point of inflection. The x value we got from before is 1/3 2a plus r. Okay, so if you say it's between r and a, you don't get the point. It's actually 2/3 of the way from r to a, and it's really difficult to come up with that answer, and I'm pretty sure nobody got this answer when they wrote this exam, but let's see how they got to that. So I'm using this diagram from before, but we want to look at the general case where this is just r0, right? Now this distance right here, r is -2, but this is a positive distance, so this distance is actually -r, okay? Which is a positive number because little r is negative. So that distance is -r, this distance is a, so the distance from r to a is a minus r. You add those two distances together. Okay, now let's look at this distance here, distance of this point. Well, it's from point R, it's -r plus 1/3 2a plus r. And if you simplify that, that's going to be -r plus 2/3 a plus 1/3 r, which is 2/3 a minus 2/3 r, which equals 2/3 a minus r. So the correct answer to this question is 2/3 of the distance from r to a. H, it says consider the special case where a equals r and b is greater than 0. Sketch this curve for a equals 1, b equals 2. So it's a bit tricky. But remember, r equals 1, that's going to be the x-intercept. And for the point of inflection, the x-coordinate of the point of inflection is 2 times a plus b. So that's actually just 1. So the point here is the point of inflection, and the x-intercept are going to be the same. Also, we got b equals 2. Recall the slope of the tangent is going to be b squared, so that's 4. So it's not going to be an inflection point like that. It's going to be a non-stationary inflection point. Okay, so it's going to go like concave down, and it's going to become concave up later on, going through the point 1, 0. So that's about it. I think that meets the requirements of the mark scheme. For a equals r, state in terms of r the coordinates of p and a. So this was a specific case where a equals r equals 1, and we got 1, 0. So you can deduce that the coordinates of both those points are always going to be r, comma, 0. Okay? It's only a one pointer, you don't need to prove anything here, but you could actually just do 1/3 times 2a. Now if a and b are a and r are the same, then you could say, actually let's just do r, let's put them both as r, then you just get r, right? So the x-coordinate is always going to be r for the point of inflection if a equals r.